All right, so I want to talk a little bit to you about number 4 for the take-home exam. I've got it pulled up here. I want to give a little bit of hint or just kind of guide you through the process for this one a bit. This problem is all about building a differential equation, and fortunately you don't have to build it. I've already built it for you. I just don't have it in the form that Matlab needs, so this is mostly going to be about translating what I've written. I give you the situation given by this little image here, 4 masses with springs connecting between them. I give you the details of these. I talk about how a solution to this problem, considering it's two-dimensional, would be positioned x and y coordinates of each of the masses over time. That's 8 independent variables, x1, y1 of t, x2, y2 of t, x3, y3 of t, x4, y4 of t. I say independent, I probably shouldn't say that. They are dependent. They depend on each other, they depend on time, they depend on all sorts of things. But there are 8 of them. Below, I have the differential equation. I set up a whole bunch of stuff that's really useful. I give you the position vectors from one mass to another. I give you position vectors from the wall to the different masses. Sorry, the remote desktop is very slow, so I'm struggling to scroll and see what's happening. These vectors are relevant in determining the forces that act between the masses. I built this all into vector equations because these things are more simply described that way. These vectors are needed to calculate the direction of the spring force, and the magnitudes of these vectors are about the magnitudes of the spring forces. So as we work our way down, this all culminates in a final set of equations. Wait for it. The scrolling ever works. Here I give you what these magnitudes represent. These formulas are not so important. If you've got vectors described, then these are just the magnitudes of those vectors, so that shouldn't be too odd. L represents the lengths. L vector is the vector that goes from one position to another. I give you the change in length, considering the fact that the springs have an unstretched length of 2. So you must subtract 2 from them. All these things are relevant for the calculation. So with that in mind, I give you all this information, and then I give you the differential equations, which are these. This is mass times acceleration equals the sum of the forces. The right side are 4 spring forces, considering each mass is connected to 4 springs. There are 4 spring forces, and here they are. Your job is to build these equations in a Matlab function file. That function file needs to be as thus. If you give it the positions, it can give you the accelerations. But if we think about that a little bit deeper, it doesn't quite work, because acceleration is the second derivative of position. We need this to be a first-order differential equation. So we're going to make a slight, distinction, I suppose. If I make a file in Matlab, we need to build a file. I'm very excited for this to work. Patience, I suppose. Okay, so for this file, it's important to realize, I'll just write this all in a comment, we're thinking about the y vector for this problem containing all of the positions and all of the velocities. I would call this x1, y1, x2, y2, x3, y3, x4, y4, and then their derivatives, v1x, v1y, v2x, v2y, v3x, v3y, v4x, v4y. This is 16 elements, 8 positions, and 8 velocities. And the derivatives of this, I'll call this y prime. This is, by the way, this is just for notes. This is not helpful in Matlab. These comments are to help us think about what y and y prime are. You will need to write a function file that generates these things. By the end of this video, I'll have generated some of it for you, so you have a good starting point. Y prime is going to be the derivatives of y. The first element of y is x1. One moment, I'm going to take a second here. I should have done this at the beginning of the video, but I'll do it now. I noticed in my last video that the font size was a little small. I don't know what type of screens you guys are looking at these videos on, so I'd like to increase the font size for better visibility on smaller screens. Go to 12 at the very least. So that should have a positive impact on readability, I would think. Okay, so the first element of y is the the first mass's position in the x direction, what I've called x1. The second element is y1, so y prime, the derivatives are, well, what's the derivative of x1? That's just v1x, the x velocity of mass 1. And then, you know, the next one is v1y. The next one is v2x and v2y and so on and so forth. It's frozen a little, so here's hoping that it comes back to. Come on, remote desktop, you can do it. Okay, there we go. So it's important to realize that these first 8 elements of y prime, let me keep going, so v3x, v3y, v4x, v4y, these are simply the derivatives of these terms up here. They're meant to be anyway, that's what they represent. They're positions up above and velocities down below. For the next 8 terms, I have the derivatives of these, the derivative of the velocities, and those are the accelerations. That's the acceleration of 1 in the x direction, the acceleration of 1 in the y direction. I still need to use semicolons here. Pardon the noise there. A1x, A1y, A2x, A2y, A3x, A3y, A4x, A4y. This line is only trying to help us visualize what we're trying to build here. We have positions and velocities of the 4 masses in our y vector, and then velocities and accelerations in our x vector. We must build a function that, if given this, we can calculate this. Come on, Matlab, you can do it. Okay. Given the top, we can calculate the bottom, and that's where all of this plays a role. This is going to be the file that describes how acceleration of the different objects, how acceleration of the different objects depends on ultimately their positions on the right side. So yes, this all describes a process you could follow if given x1, y1, x2, y2, x3, y3, x4, y4, you could calculate these vectors, their magnitudes, these vectors, their magnitudes. The deltas are calculated in this fashion, and then the matrix equation, well, it's not really a matrix equation, is it? The big equation that tells you what x1 double dot is just, it's the x component of this equation. We've got to divide by the mass here to get x1 by itself, x1 double dot. But yes, if given the positions, you can calculate all of these things. If you can calculate all those things, then you can calculate x1 double dot. That is the basic idea. Of course, getting the first 8 elements of y prime is trivial. Given this, can you find this? Yeah, I mean, it's already there. So the first 8 elements of y prime are just the last 8 elements of y. So we're going to incorporate that in our solution. So I'm going to build this function file, just a start. It's going to be dy dt is equal to a function. I'm going to call this spring system ODE of t comma y. And I'm going to do the following things first. So that I can use familiar vectors, I'm going to go ahead and create a bunch of new variables. Keep in mind, this is given to us by a user. Someone's going to plug in things into this function, and we need to output dy dt. So for y, I'm just going to say that we're going to make a new variable. I'm going to call it, say, x1. I tried, x1, and that's just equal to the first element of y. What I'm doing right now is not necessary, but I think it's going to be helpful. x2 is equal to y3, x3 is equal to y5, x4 is equal to y7, y1 is equal to y2, y2 is equal to y4, y3 is equal to y6, and y4 is equal to y8. I'm just putting all of this down here so that I can use, I could just use these variables on the right, y1, y3, y5, y2, all that stuff, but I kind of want these variables on the left to exist because I can use them. So I'm going to go ahead and, first of all, I put these all in different lines, but I find that to be a little bit crowded, so I'm going to go ahead and put these all in the same line. You're allowed to do this. I'm putting them all in the same line so that Matlab, so it's not a 10-line code already. That's the main reason. So the next thing I'm going to do is I'll get started with just one of these equations. I'm going to create a variable. I'm going to call it L12. I'm going to use a capital L so that I can differentiate it from its magnitude, but you don't have to. You can do whatever you wanted here. I'll say L12 is equal to, it's a 2-element vector, and here it is. 2 plus x2 minus x1, 2 plus x2 minus x1, and the second element is, very excited, y2 minus y1. I'm making it a column vector because this is a column vector, everything's a column vector, so that's what I'm choosing to do. That's L12. And I'm going to just make the rest of them. Just go, 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 make them all. When I'm done, I will be able to have the accelerations that I will solve for using this big expression on the right. So let's jump all the way to the end. At the very end, we need to tell them what dy dt is. That's the thing that we were generating. And I'm going to do this 8 elements. Well, I can do it 2 elements at a time, 8 elements at a time, whatever. I'm going to do the first 8 all at once. What are the first 8 elements of dy dt? Well, that's these. v1x, v1y, v2x, v2y, and so on. Where can we find those in y? They are the last 8 elements. So dy dt 1 through 8 is just y 9 to 16. dy dt 9 to 16 is more complicated. dy dt 9 to 16 is going to come down to all of these. And I would probably make them 2 at a time. So I would do 9 and 10 first. And it would be k divided by m times, well, let's write this out. What does it say? I'm going to call it dwx1. We lost the video. I'm not quite sure where we lost it, but I'm just going to keep going. So what I mentioned was that I am going to build all the acceleration terms. Those are the next 8 elements, elements 9 through 16 of dy dt, but I'm going to make them 2 at a time because these equations are in terms of them 2 at a time. So I'm going to make these 2, x1, y1. This is a 2-element vector already, so to get these 2-element vectors, I'm just going to just calculate all of this at once. I need to divide by m to isolate them, so I'll do that first. That's k divided by m. Let me go ahead and make this like half the screen so maybe I can actually do this all at once. K divided by M times, I'll call this dwx1 divided by wx1 times wx1. This is literally what my code says. Plus dwy1 divided by wy1 times wy1 plus dl12 divided by l12 times l12 plus dl13 divided by l13 times l13. Okay? The important thing to realize about this expression is I would need to calculate all these things. What is this? What is this? What is this? And all that detail goes up here. Calculate all of the rest of the stuff in terms of, you know, x1, y1, x2, comma, dot, dot, dot. Like, in terms of all the positions. In this expression, I already know one of the things. L12 is something I've already calculated. It's right here. And L12 is going to be the norm of L12. It's the length, the magnitude. And then dL12, it says in the homework file that that's equal to L12 minus 2. So you can see that I'm going to be building all of these things so that they can be put inside of this expression. The thing on the right side is a two-element vector because L13, L12, Wy1, and wx1, I don't know if I read that right, let's say that, because wx1, wy1, L12, and L13 are all two-element vectors themselves. So this is a two-element vector, this is a two-element vector, and specifically it is a1x and a1y, the I hat and the j hat components of the acceleration in x and y. So then I just need to go to the next one. On this code, there's a lot of stuff missing. There's a lot of stuff missing in here, but ultimately it is follow this advice, follow these equations, put them in, so that when you write lines of code that look like this, they're all known. They've all been calculated in advance. Take a look at the other video for how you should then take this code and then call this function in a separate ODE file for your result. That's all I have to say about this. If you have any questions, I'll be available this week via Zoom, email, whatever you need. They closed campus today, so I'm not quite sure what's going to happen with that moving forward. I've been told not to have face-to-face meetings with students anymore this quarter, so we'll have to do all of our contact remotely. Although I'm sure that works for all of you. Staying home is, more or less fine. All right, well, hope you all have a good week. Let me know if you have any questions, and I'll see you next quarter, I hope.